All right, so you were to turn off the video and try to do the mean and the standard deviation on your own. I ended up breaking videos, so this is what I've put together, and I'll explain now how we did that. So we started with the probability distribution function for a single roll of a die, with 1 through 6 being our options and 1/6 being the probability for each number on the die. So multiplying the x times the p of x's, we get 1 times 1/6, 2 times 1/6, 3 times 1/6, so on and so forth. So we get 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. If you're doing this by hand, it's much easier to keep these in terms of 6. Adding 1, 2, 3, 4, 5, and 6 up, we get 21, and those are sixths. Now going over to do the x squared times p of x's, 1 squared times 1/6, 2 squared times 1/6, 3 squared times 1/6, 4 squared times 1/6, 5 squared times 1/6, and 6 squared times 1/6. And adding all those up, 1, 4, 9, 16, 25, and 36 gives me 91/6. So my mean is the sum of the x times p of x's, and 21/6 is equal to 3.5. And if you remember right, I talked about if we took a look at the distribution here, that the balancing point in the middle, that would be between the 2 and the 3 bars, and that would be at the 3 and the 4 bars, and that would be at 3.5. Now this variance is the sum of the x squared times p of x's minus the mean squared. So 91/6 minus 21/6 squared. So I need to build the higher term here. So multiplying by 6 here, multiplying by 6 here, is going to give me 546/36, and squaring 21 and squaring 6, we get 441/6. Subtracting the numerators, because we have a common denominator, I get 105/36. And then I need to take the square root of that value in order to get my standard deviation. So the square root of 105 divided by 36 is approximately 1.707, or approximately 1.7. So that's our mean and our standard deviation. All right, now moving forward, what we want to talk about is an expected value. An expected value is nothing more than mean. And this is it's application of the mean used in something called decision theory. So we're going to talk about this example here. A game is to be played with a single die that you assume to be fair. In the game, a player wins $20 if a 2 turns up, $40 if a 4 turns up, and loses $30 if a 6 turns up, and neither wins nor loses anything if any other number turns up. Follow the step-by-step process for finding the expected profit and playing the game by answering each of the questions that follow. So we're going to start out by thinking about our basic die rolling probability distribution function. And the probability distribution function, that's the one that we just did. So 1 and 2 and 3 and 4 and 5 and then a 6, and then each of these values being a 1/6 here. So just let me get the little distribution made here so that we have this to base our answer upon, because this is where it's going to come from. So now what I have is I have this game, and I am looking at not the values here for the x's, but I'm actually looking at the payoffs. So if I get $20 or $40 or lose $30 or get 0. So I'm going to start with ordering these. So I get 0 payoff, I get a $20 payoff, I get a $30 payoff, or I get $40 payoff, sorry, a $40 payoff, or I lose a $30. So that's my values there. So what it says is that If I win, it's a 2 that turned up. Well, I need the probability of a 2 turning up. Well, that would just be 1/6. So this probability here that goes along with this is 1/6. Now I'm going to win, oops, not that one, that's 0. Sorry, my bad. That's 1/6 right there for the 20. Now if I win $40, a 4 turned up. Well, there's only that 1/6 probability that a 4 is going to turn up. So that's going to be the probability associated with that. So this is here and this is here. And then if a 6 turns up, I'm going to lose, and the 6 turning up is going to be a probability of 1/6 as well. So that leaves a 5 or a 3 or a 1 turning up where I wouldn't win anything, and that probability is 1/6 plus 1/6 plus 1/6, or 3/6. And you can simplify, of course, that to 1/2, but again, because I'm going to need to be multiplying to find my expected value, I probably won't want to. So this is my probability distribution of a single roll of a die, and then this is my probability distribution function for my game, and x's are my winnings, and the probability are derived based upon here as shown. And now I want to find the expected profit. Now in this one I have to multiply my x times p of x's, find my mean, right, because that's what expected value is your mean, just like I would have before. So 0 times anything is 0. 20 times 6, so we have 26. And then 40 times 1/6, so I have 46. And then I have 30 times 6, or negative 30 times 6, I should say. And now I want to add these all up. So I have 20 and 40 is 60 minus 30, which is 30, and 36 is the value, and 36 is equal to 5. So the expected profit, the expected value, which we label as E of x, is equal to $5. Now the assumption here is that I'm just playing, I'm not actually playing a game where I have to pay. This is just the expected profit in the long run. So if I continue to play this game over and over and over again, I would expect to win $5 in the long run. Now we know, of course, that that every time you play, right, you're probably going to win something or maybe not win anything. So if you think about it, the expected value being $5, that doesn't seem to make sense. But remember, you are looking at this as a long run probability if you continue to play and play and play. So this one, the minus $30, right, every once in a while you're going to lose, but then you're going to end up making money and sometimes breaking even, and just this losing every once in a while. So that's where the expected value of $5 comes in. All right, now you're going to do the same thing for this problem here. So you want to think about what would happen in the probabilities, and then create a probability distribution function for the tickets, and then go ahead and make the probability distribution for the wins and losses. All right, so you should turn off the video, see if you can do this on your own, and then come back and see how you did. All right, so taking a look at this, in lottery there are 200 prizes worth $5, 20 prizes worth $25, 5 prizes worth $100, and if there are 10,000 tickets sold, what is the expected winnings for this lottery? So the expected winnings, we have to first of all make a very basic probability distribution function based upon the X, which is the amount of money that you win. So if I win $5, then this is going to be possible based upon 200 tickets having that $5 worth out of the 10,000 that are sold. So if there's 5 out of 10,000 here that have a $5 worth. And then there are 20 prizes that are worth $25, so 25 here. I'll have 25 out of the 10,000. And then the next problem here, next part, I have 5 prizes that are worth $100. And so there's my $100. And that's 5 of them again. Oops, this first one I said 5. That was bad. This is not 5 of them. There were 200 of them that were worth $5. So this is 200 out of 10,000. And this one is 5 out of 10,000. All right, now there's something missing here, and that's the fact that you might not win anything at all. And there are a bunch of tickets that don't have that. So if there are 225, 230 that have winning values, then we have to also think about how many don't have any winnings at all. So that would be the 10,000 minus the 230 here, and that's out of the 10,000, and that's just the idea of a complement. And that way, when we add up all the probabilities, we get a total of 10,000. So now we'll go ahead and we'll find the expected amount to pay based upon this. Now, if you have a problem where you actually have to play to pay the game, then you take the money that you would win and subtract the money you have to pay to get a net value here, and that's how you find your expected winnings. Just in case you have ones like that, because the Triola book, the new expected value problems, that's exactly how they're set up. So we have 5 times 200 here, so 5 times 2 is 10 with 2 more zeros, and then this is out of the 10,000. And then this one, 25 times 25, that's 625, and that's again out of 10,000. And then 5 times 100, that's 500, and that's again out of 10,000. And then we have to do the 10,000 minus 230, so 10,000 minus 200 would be 9,800, and then 9,770 is what we end up having here, right? And we could go back and add it up, 0 and 0, 3, that's a 0. Carry the 1, and that would be a 0, and carry the 1, and that would be 9 plus 1, which would be 10,000. So we got that right. And this, of course, has 0 as our probability times our expected winnings. All right, now 1,625, 2,125 out of 10,000, and that division has 4 zeros here, so that's moving the decimal 1, 2, 3, and 4 places. So my expected value here in the long run, playing this game, if there's no cost to play it, or what could be deemed as the value of a ticket, should be approximately 21.25 cents for the ticket. Now, of course, that's not how much the tickets would cost, right? Because they want to make money, so they would have a bigger value than that. All right, moving on. We have a scenario where we could use a factor tree as a method for finding the probabilities. So let's take a look at this example here. Using this factor tree. So we have the probability that a radio produced by Acme Radio Company being defective is a half. So because it's an even probability, a half-half, we can use the factor trees. If you don't have equally likely probabilities, it's a little bit trickier. It can be done, but we wouldn't want to do that. So we have a defective radio, and we'll call it a good radio. And so we're going to be choosing 4 out of these. So what I need